All right, going to start on activity number one for our last unit here on probability and some basic counting principles. First paragraph there just talks about rolling two dice and the results used in a game called backgammon. Intro to probability, because of the symmetry of the pair of dice, each side is equally likely to end up on top. It's easy to find the probabilities of various outcomes as you work on the problems. Look for how can you find and organize the probabilities associated with these random events. So we've got the table, and here it's filled out. That already has our different outcomes. So the first question, what does entry 4, comma 5 in the chart mean? So 4, 5 means 4 was on the red and 5 was on the green. And then as we view the chart, looking at how many total possibilities there are, we have 36 total possibilities. 6 different possibilities on the green, 6 different possibilities on the red. And I understand these are blue, but that was the color marker that we had. Probability rolling a 1, comma 2, that's a 1 on the red die and a 2 on the green die, is going to be 1 out of 36. Happens one time. 1, comma 2 is this one spot right here. So here we're saying that the order does matter because they're different color. So when we look at the 1, 2, that's different than 2, 1, which is the next question, which is a 1 out of 36. And a 4, 4, also 1 out of 36. Again, the idea there is that we have a sample space. That sample space is the possible outcomes for a random event. All 36 in that sample space are likely to occur, so they are equally likely events. And then to find the probability, it's the number of successful outcomes divided by the total number of outcomes. So we'll look more at that as we continue to go through. All right, so this is what I was just trying to summarize there. Number of successful outcomes over the number of possible outcomes. So our number of possible outcomes is going to be 36 because all of those outcomes are equally likely. Probably want to have that chart on hand as you continue through the rest of it to make sure that you can pull those probabilities off of there. So probability of getting doubles, there are 6 doubles out of 36 possibilities. So we can simplify that to 1/6. Probabilities you can write as a decimal, percent, or as a fraction. So any of those would be a fine way to write a probability. Sum of 7. So how many times do we find a sum of 7 in that chart? There's 6 of them. So again, 6 out of 36, which simplifies to 1/6 of the time. Sum of 11, there's 2 of those, 5, 6, and 6, 5. So 2 out of 36 chance. So 1 out of 18. At a 3 on at least one die or a sum of 3. So as you look through that chart, you've got the column that has a 3. You've got the row that has the 3. You've got the 2, 1 and the 1, 2. And make sure that you don't count the place 3, comma 3 twice. So that one, there are 13 total out of the 36. As you look at that one. Doubles and a sum of 10. So that means that you have to do both of those things, doubles and a sum of 10. So doubles and a sum of 10 is going to put us at 5, 5. So there's only one of those. And then doubles or a sum of 10, that one's going to end up being 8. And then a sum of 10, or doubles, there are 6 of those. And then sums of 10, there are 4 of those. There are 2 of those, that are not doubles. So 6 plus 2 ends up being 8 out of 36, which simplifies to 2/9. List the sample space for the following event. So now we're just understanding what a sample space is. So that is listing the possible outcomes, flipping a coin 2 times and recording the results. So there are 4 different possibilities. 3B, the number of girls in a family of 4 kids. So this is the number of, so when our sample space is the number of, we should be giving numbers as our list. So I don't want you to list the G, G, B, and all of those different things. It is just says sample space is the number of girls. So the number of girls could be 0, 1, 2, 3, or 4. And I think we're just talking about the kids here. So I did not include the parents in that one. Okay, back to the dice. Probability that the sum is not more than 9. So it can be 9 or less. So as I look at that chart, there are 30 of those. Maybe even I could count, it might be easier to count the ones that are more than 9, and there would be 6 of those. So 30 of them would not be more than 9. Sum is at least 9, so 9 or greater. There's 10 of those. Sum is 2 or 3. There's 3 of those. 1, 1, 1, 2, and 2, 1. Greater than 3, so there's 33 of them that are greater than 3. And at least 3 would be 35 of them. There's only one of them that is not at least 3, and that would be 1, 1. And that's the last one, less than 3. All right, a little bit more vocabulary here. Relative frequency versus probability. So relative frequency is the outcome of an experiment where you keep track of the number of successes for the total number of trials. For example, if you flip a coin 100 times and get 48 heads, the relative frequency is 48 out of 100. The relative frequencies are similar but different from probabilities. Both yield values from 0 to 1, but the meaning of the values differ. A relative frequency of 0 means that the event has not occurred. Probability of 0 in a finite sample means the event is impossible. So the relative frequency of 1 means that the event has occurred in each known trial. In contrast, probability of 1 means that the event must occur. So the difference here is relative frequency is what did happen in an experiment. Probability is more what should happen, what we would expect as we do more and more trials to get closer and closer to that particular value. So relative frequency is during an experiment what happened. Probability is what we would expect to happen. So you have a 1 in 8 chance of flipping 3 heads in a row. That's probability. So that is just giving a statement as far as what should happen. Part B, I flipped a coin a set of 3 at a time. And in 4 of the 50 sets, I had 3 heads in a row. So that one is relative frequency because that is what did happen. So that's the difference. That's how we differentiate between those two vocabulary terms. All right, getting into the addition rule. So we're going to skip over number 6 because that was one that we would have done kind of in class. But up top there, we talk about what that addition rule is. So you're asked to find the probabilities of the sum of 2 or 3. And to do this, we can just add the probabilities together. Probability of getting a 2 was 1 out of 36. Probability of getting a 3 was 2 out of 36. So we can add those together, and we found a 3 out of 36 chance of rolling a sum of 2 or 3. So I want to see if that actually works for all of these different situations. Under what conditions can you add individual probabilities to find the probability that a related event will happen? So as we go to number 7, that's where we're going to flip to. We're given a table of values. The table is percentage of high school juniors who say they engage in various activities at least once a week. Many reported doing multiple activities. So use the table to help answer, if possible, each of the following questions. If it can't be answered, explain why not. So first one's probability that a randomly selected junior takes sports lessons at least once a week. So that's how these students responded. Take sports lesson, 22.6 of the students said that. So that seems like we can just grab that number off the chart. What is the probability randomly selected junior works on hobbies at least once a week? Again, just go to our chart. We can grab that one. Seems to work. What is the probability that a randomly selected junior takes sports lessons at least once a week or works on hobbies at least once a week? So sports lessons and hobbies, that's these two numbers here. So up here, we just added those values. Does it seem to make sense to just add these values here? Well, it comes down to how they asked the question. Many reported doing multiple activities, and all that they asked was, do you engage in these activities at least once a week? So if I add those, I'm going to have some students that I'm counting twice, the students that do both of those things. And I don't know how many kids that is. So I cannot answer that question. Same thing's going to be true with part D. The or part, because I don't know what the overlap is, I don't know the students that do both of those, I cannot answer that question. Number 8, could I come up with a new question that I would be able to add. So what characteristics of a table would make it possible to add the probabilities to answer an or question? If double counting students was not possible, that would work. If the events are mutually exclusive, we'll talk about that vocabulary term. If you make students pick one event, so if I were to say, what is your favorite thing to do? Or what do you do the most often? So where they can only give one answer. So that would make it so there would not be any overlap in these percentages. And then I could just add those. All right, so let's look at some numbers here where we have a whole table broken down. Minnesota student survey asked teens questions about school activities and health. Ninth graders were asked, how many students in your school are friendly? Number of boys and girls who gave each answer are shown in the table below. So a bunch of numbers in there. How many students in your school are friendly? All, most, some, a few, none. So you can see how the boys answered. You can see how the girls answered. They totaled up each of the answers. All, most, some, few, none. They totaled up the boys and the girls on the bottom. All right, find the probability that the student said that all students are friendly. So all are friendly. That's our top row. So 783 out of 49,210. All are friendly. Part B, find the probability that the student said most are friendly. So most are friendly. So 27,368 over 49,210. Find the probability that the student who answered is a girl. So now we're looking at the column, 25,211 out of 49,210. Find the probability that the student is a girl and said that all students are friendly. So because I have all of this data in the table, I can just look at that cell right there, 303 out of 49,210. All right, think about how you would find the probability that the student said that all students are friendly or said that most students are friendly. Can you find the answer to the question just using your probabilities from parts A and B? If so, how? If not, why not? All right, so I want to find if they said all are friendly or most are friendly. So A and B, those are the two probabilities. So in this instance, would it be okay to add those two together? And the answer is yes. You can add those together because there is no overlap. Student could not have said all are friendly and also have said most are friendly. So we can just add those together and we get our probability. I think I've got a decimal point wrong in there. Well, I think it's supposed to be 0.5721. All right, part F. Think about the probability that a student is a girl or said that all students are friendly. If you were not given the original table above, so we didn't have the whole table, could you answer the question just using your probabilities in parts A and C? So the reason why they're saying that is because A is all are friendly and C is answered, the person that answered is a girl. So they're asking, can I just add those two together? And the answer there is no, we're going to be double counting the girls that said all are friendly. So if all I had were A and C, the answer would be no. I cannot answer that question. 2, can you find the answer if you also use your probability in part D? If so, show how. If not, why not? So on this one, if they also give me this number, then I can, because the people that I'm double counting, the girls that said all are friendly, are listed right here. So what I can do is add my part A and part C and subtract off the D because those people got counted twice. So there's our setup. All are friendly plus all the girls minus the girls that said all are friendly because they're counted twice. And there's our answer. So addition rule, a little bit different because we have to take off the ones that got double counted. All right, so understanding the idea of double counting comes up with the thought of events being mutually exclusive. So 2 events are said to be mutually exclusive or disjoint if it is impossible for both of them to occur on the same outcome, Which of the following pairs of events are mutually exclusive? You roll a sum of 7 pair of dice, you get doubles on the same roll. Can't happen. So those are mutually exclusive. I can't get doubles and roll a 7. Not possible. Could I roll a sum of 8 and roll doubles? Yes, I could. That is not mutually exclusive. Both of those things happen when I roll a 4 and a 4. So just understanding what that means. So there would be some overlap there. A couple of other examples. Isaac wears white shoes to class today. Isaac wears black shoes to class today. We're saying the primary color, most of the shoe is white, most of the shoe is black. That would be mutually exclusive. He's not going to be doing both of those. Fern owns white shoes. Fern owns black shoes. This would be not mutually exclusive. She could own both of those because the word here is own as opposed to wearing today. So not mutually exclusive for part D. Part C and D, those are similar to what we would have done on number 6 if we were meeting face to face. All right, so let's go through some mutually exclusive and what that looks like. Suppose events A and B are mutually exclusive. Which of the Venn diagrams better represents the situation? So mutually exclusive means there's no overlap. Rolling doubles, rolling a sum of 7. That would be the Venn diagram on the right. And what does the fact A and B are mutually exclusive mean about the probability of A and B? So the probability of A and B means that they are both happening at the same time. There's no overlap. This is mutually exclusive, so that will have to be 0. There is no overlap. It's none. When A and B are mutually exclusive, how can you find the probability that A happens or B happens, or both happen, which we know isn't going to happen? So probability of A plus probability of B, we can just add those together. It's like going back to the sum of 2 and the sum of 3 on those dice. We can just add those together since there's no double counting. Write a symbolic rule. So here's a symbolic rule. Probability of A or B equals the probability of A plus the probability of B. That's the addition rule for mutually exclusive events. Number 12, suppose two events are not mutually exclusive. So this one, which diagram represents this situation, this one, the one on the left, because there is overlap. So I could have all of the doubles over here. 1, 1, 2, 2, 3, 3, 4, 4 would go in the middle. 5, 5, 6, 6. And then the other ways that I could roll an 8 would be out here. So 2, 6, 6, 2, 3, 5, 5, 3, and then 4, 4 is in the middle. So that's our overlap idea, that it would be both doubles and a sum of 8. What does the fact that A and B are not mutually exclusive mean about probability of A or B? Where is the probability represented on the Venn diagram? So here I have some overlap, which would be counted twice if I use this formula. So I can't just add this circle and this circle because I counted this part twice. Describe how I can modify the rule. So now to complete this rule, I'm still going to add them, but now I can subtract off the overlap. So probability of A and B, that's probably that they are both happening. That's the probability. That's the part that I'm counting twice. All right, so let's see if we can use that rule. As we go through, notice actually before I flip that this rule would still work for this one, because if I subtract off the overlap in this one is 0. So instead of trying to maybe memorize or remember 2 rules, I can just remember this one. I add the 2 probabilities together and I subtract the overlap. I subtract the overlap, and that's an easy one up here because there isn't any. So maybe just remembering that one rule will be helpful as we go. All right, so first one, find the probability that you get doubles or a sum of 5. So I have it set up doubles, there's 6 out of 36. Sum of 5, there's 4 out of 36, minus the overlap, which is 0. So I got 10 out of 36. Get doubles or sum of 2. So it's 6 out of 36 are doubles. There's 1 sum of 2. There is 1 overlap. So 6 plus 1 minus 1 over 36. So I get a 6 over 36. Find the probability that the absolute value of the difference is 3, or you get a sum of 5. So absolute value of the difference is 3. So that would be like getting a 4 and a 1 and a 4, 6 and a 3 and a 6, 5 and a 2, 2 and a 5. So those, there are 6 of them. Sums of 5, there are 4 of those. And then there are 2 of them that overlap. So the 4 and the 1 and the 1 and the 4 would have been counted twice. So I subtract those off and I get 8 out of 36. Finally, probably the absolute value of difference is 2. So here I would have 6 and 4 and 4 and 6 and 5 and 3 and 3 and 5 and 4 and 2 and 2 and 4 and 1 and 3 and 3 and 1. And there are 8 of those. Sum of 11, there are 2 of those. And there are none of those that are the same. So add the individual probabilities, subtract the overlap. All right, so to summarize, give an example of 2 mutually exclusive events different from those in the activity. Lots and lots of different things for that. I said using a deck of cards. Draw a red card and a spade from a standard deck of playing cards. Your birthday this year is on a Friday. Your birthday this year is on a Saturday. Things that could not happen at the same time. How do you find the probability that event A and B, A happens or B happens if they are mutually exclusive? That's our addition rule. And then how do I have to modify it if they're not mutually exclusive? So if there is overlap, we can subtract off the overlap. So this is the intersection. That's what the and part means. So we subtract off what they have in common. And I still go back, notice this formula works for part B as well. The overlap here is just going to be 0. So I could actually just use the same formula and put it here and just realize that the overlap in mutually exclusive situation is going to be 0. All right, so that's a quick lesson there, activity on probability and some counting. And we'll have one more activity on some counting principles as we finish up this particular chapter.